Hello and welcome. Today, we're diving into one of the most powerful concepts right at the heart of the Linux kernel, modules. You can think of them as the secret sauce that makes Linux so incredibly adaptable and efficient. Honestly, if you want to understand Linux, you've got to understand modules.
Okay, so let's just jump right in with the big question. Think about it for a second. Linux runs on literally everything, from massive supercomputers all the way down to your phone, your smart TV, maybe even your toaster. How on earth does it manage all of that different hardware without becoming this gigantic, slow, unfixable beast? Well, this is the exact problem that kernel modules were created to solve.
To really appreciate just how elegant this solution is, we first have to understand the problem. So the old way of thinking things, the alternative to a modular system, is what's called a monolithic kernel. That's where every single piece of code, including every possible device driver, is all compiled together into one single massive kernel file.
Just try to picture that. A kernel with drivers for every single graphics card, every network chip, every weird USB device ever made. The file would be enormous. It would chew up a ton of memory, and anytime a tiny bug was fixed in just one of those drivers, everyone would have to recompile the entire kernel. It's not practical at all. A totally different approach was needed.
And that, right there, brings us to the brilliant solution that Linux adopted, this idea of loading code on demand. So instead of that clunky one-size-fits-all approach, the kernel can now just load the specific pieces it needs right when it needs them. This simple idea completely changes the whole game.
So this is the heart of it. A kernel module is basically a plugin for your operating system's core. You can load new features, new drivers, new file systems, whatever you need into a running system. And when you're done, you can just unload them. And the best part, no reboot required. It's dynamic, it's flexible, and it is incredibly efficient.
And look at how versatile this is. Yeah, the most common use is for device drivers, for your sound card or your Wi-Fi adapter. But almost anything can be a module. Need to read a DVD? The kernel can load up the UDF software file system driver. What about major security frameworks like SE Linux or AppArmor? Yep, those are modules too. This idea is woven into the very fabric of the kernel.
Okay, so that's the theory. But how does this all work in practice? Let's make this whole concept a little more tangible and walk through how you'd actually create, build, and use a simple external module.
Believe it or not, getting started is way simpler than you might think. You just write your code in C like you normally would, then you just have to tell the kernel's build system, it's called kbuild, that you want this thing to be a module. For a single file, that build file is literally one line. That's it.
Then you just run a standard make command. Now, we're not going to get into the weeds of every single flag here, but basically you're telling the build system, hey, use the source code for the kernel I'm running right now and build the module that's sitting in my current directory. What you get at the end is a .ko file, your compiled kernel object all ready to go.
To get it running, you use a command like insmod. And here's something that's really cool. You can actually pass parameters to the module when you load it. This lets you configure it for specific hardware settings, maybe an I/O address or an IRQ line, without ever having to recompile the code. It's super flexible.
And that dynamic control doesn't stop there. Once a module is loaded, the kernel actually exposes a bunch of its parameters right in the /sys file system. You can just browse to that directory and look at them. And in some cases, you can even change those values on the fly, altering how the module behaves without ever unloading it.
So, building an external module, or what developers call an out-of-tree module, is totally possible. But it is absolutely not the preferred way to do things. And to understand why, we really need to dig into a core philosophy of Linux kernel development, the huge, overwhelming preference for keeping code in tree. Okay, so this is the crucial difference. When your code gets accepted into the main kernel source tree, it becomes part of Linux itself. It's available to everybody, it gets reviewed and improved by developers all over the world, and this is the big one. When the internal kernel interfaces change, other people will fix your driver to keep it working. Out-of-tree modules, you get none of that. You're on your own.
Now, why is that last point so important? Well, because the kernel developers made a very deliberate choice not to have a stable internal API. I know, that sounds crazy at first, but it's what lets them constantly refactor and improve the kernel's core without being tied down by old, clunky interfaces. This focus on long-term quality and innovation is exactly why being in-tree is so vital for a module's survival.
But all of this power and flexibility, it introduces a really serious challenge. I mean, if anyone can just load code directly into the heart of the operating system, how do you maintain security? How do you keep the system stable? This brings us to a really fundamental question of trust. The kernel community has a very, very strong stance on this, and it's captured perfectly in this official statement. You see, the core philosophy of Linux is all about openness. And these closed-source binary-only modules, well, they go against everything that philosophy stands for. And look, this isn't just about some abstract philosophy. These binary modules create huge practical problems. When a system crashes and there's a closed-source module involved, it's a total black box. Kernel developers have no way to debug it, and that hurts users. Not to mention, distributing them often exists in a really murky legal gray area when it comes to the kernel's GPL license. So, this brings us to the main technical line of defense. To fight the risk of loading unknown or even malicious code, the kernel uses module signing. During installation, modules are signed with a cryptographic key. Then, before loading any module, the kernel checks for a valid signature. If it's not there, or if it's invalid, the kernel can just refuse to load it. It's a critical security feature. So, we end up right back where we started. Kernel modules give Linux this incredible world-changing power and flexibility, letting it adapt to pretty much any hardware you can imagine. But that power comes with these inherent security risks, and managing those risks requires both community pressure and technical safeguards, like module signing. It's this constant balancing act, and it's truly one of the most fascinating tensions in all of software engineering.